So let's talk about an application. This time we're going to talk about rates of change. And you may remember from physics there's been a note about average velocity. And average velocity, as we know, is a change in distance. We sometimes say change in displacement over change in time, right? Displacement over time. And in this case, the change or displacement is delta S. We say S of t. We always identify S in mathematics here, anyways, in this textbook, as a position function, right? So this is a position function, and it tells us what position an object is in, whether, let's say, it's above the ground or a particle moving in the plane. So this is our position function. S is our position function with respect to time, t. So how do we get that? Well, if S is our position function, this delta S means that we've got the position at some time t and the position at some time t plus a change in time. Well, what does that mean? Let's take an example right here. Let's say that we have this equation for a billiard ball that's dropped from a height of 100 feet, where its height s at time t is given by s of t is negative 16 times t squared plus 100, where s is measured in feet and t is measured in seconds. You can tell that, for example, s of 0 at 0 seconds at the moment when the ball is released is equal to 100 feet above the ground, right? So that's exactly what we mean. We want to find out, well, what would be its average velocity over the time period from 1 to 1.5 seconds. What we're really saying right here is that at time t equals 1 second, to the time period 1.5 seconds, so we could say, well, t plus delta t, right, this is the later time, is 1.5 seconds. Well, we could pretty easily figure out what our position was, right, because we were saying, well, s at
Did
so our position at time 1.5 seconds, right, using our formula above, minus our position at 1 second, divided by that change in time, what we're really saying right here is that the change in position from t plus delta t minus s of t over delta t, right, that's going to go to, that's going to give our average velocity. So let's see, well, what do we got? S at 1 second would be equal to negative 16 times 1 squared plus 100. And we know that that's equal to negative 16 plus 100. Negative 16 plus 100 would be 84 feet. And then we would take S at 1.5, and we know that at 1.5, that's 16 times 1.5 seconds squared plus 100. And I got out my super cray computer. Actually, I worked this out by hand, but what I got was 64 feet. 64 feet. And our change in time, well, our change in time is equal to that difference in the time period of 1.5 to 1 second, which is 0.5 feet, seconds, pardon me. And so our average velocity right here is going to be 84 minus 64. Boy, those don't look like 84s and 64s. I guess I've got a leaky pen. Delta t. So we've got 84 minus 64 divided by 0.5, and doing a little bit of math right here, that's 20 divided by 1/2, which we know works out to be 40. And so our average velocity over this time period is 40 feet per second. And that's well and good for us, right? Because that's an average velocity, but we look at that and compare that to something called instantaneous velocity, because our velocity is changing, right? We know that due to gravity, the ball is going to accelerate as it goes down, right? As it heads in the downward direction. So let's say we're interested this time in finding the instantaneous velocity at t equals 2 seconds. Well, in fact, we could say this. If we took some small time period, delta t, and we worked out a position function for whatever s of 2 is and 2 plus delta t, and we let delta t approach 0, we would be fine there. But where did we see this before? Well, this is our limit process for finding a derivative. And in fact, it turns out that our derivative is the position function for instantaneous velocity, right? So the derivative of our position function, s prime, is our velocity function. So, well, let's work out what happens there. To find our instantaneous velocity, we're going to take our derivative, s prime of t. What is s prime of t? Well, s prime of t is the derivative of negative 16 times t squared. That's negative 16 times 2t to the first plus 0 by our derivative rules. S prime of t is equal to negative 32t. And so if we're interested in the instantaneous velocity at 2 seconds, s prime at 2 is going to be negative 32 times 2, and we get a result of negative 64 feet per second. Right? Negative 64. What is that negative? Well, that negative indicates that our ball is heading in the downward direction. So it is velocity in the downward direction. That's the way that we handle velocity right here. We're going to say a negative value will equal downward direction. A positive value would be upward. Clearly, this is just dropping, so negative 64 feet per second seems like a reasonable answer in this case.